something like that now. So a long time, right? She got her master's degree at Peking University in China and then did her PhD at George Mason University. Another alum from George Mason. Worked for a few years after that, or between, I don't remember.
2 years.
For 2 years after your PhD, and then came to Wisconsin after that, right? So we're very happy and fortunate to have her here, and I think you'll see why based on this presentation today. So thank you very much, and I'll turn it over to you.
Thank you, Paul, for the great introduction, and so glad to see some of the familiar faces, including from my department, and also from where I graduated. Well, again, I'm Qunying Huang from the Geography Department, and I'm so glad to be here sharing my research on rapid disaster mapping and damage assessment with big sensor data and the GeoAI with the case studies focused on the wildfire and the floods. So basically, first let me briefly introduce my research theme, which is centered on spatial data science and GeoAI, with application focused on human mobility and the interaction as well as natural hazard, which both contribute to unfolding the social equality and environmental injustice issues. I also developed different machine learning and GeoAI models to examine urban perception, study urban informatics such as detect the urban land use, land cover change, and measuring urban environmental facts such as the wellness, liability, and the playability of the community and the neighborhood. Recently, I developed a strong interest in leveraging machine learning and different technology for digital and sustainable agriculture. For example, utilize remote sensing UAV techniques image for precision agriculture applications. First, let me briefly introduce during the natural hazard, we rely on two data sources for developing different disaster mapping and damage assessment products and tools. The first one is physical sensing, for example, from the satellite UAV observation as well as from the sensor networks, GPS tracking, driver vehicle, collect Google Street View image, taxi drivers. And second, we also have a social sensing, which we call passive data collection from social media platforms such as Twitter, Flickr, SafeGraph, Wikipedia. And in my research, I rely on both data sets. For example, I utilize PlanetScope Sentinel-2 data sets to do flood mapping. I utilize Ghost Bears data product to do active fire detection and mapping. For ground sensor network, I utilize USGS observation station for flood mapping as well. And I have utilized GPS tracking, driving vehicles to study human mobility, urban perceptions. In the last, I would say 10 years, I also collected a large number of geotagged trees, flickers, mobile phone records from SafeGraph to do different application as well. Now let me first introduce the challenge and the potential solution from my research to indicate how we can better leverage physical remote sensing data and machine learning for rapid disaster mapping and damage assessment. Here I will utilize flood mapping as an example to illustrate the challenge of remote sensing and machine learning for disaster mapping. Since I would say the challenges for remote sensing image analysis and integration are quite similar across different applications. The first challenge is heterogeneous image background from the urban land structure and casted on the entire flood mapping product, resulting the noise information make it difficult to identify flooded area for image segmentation of object detection. The second one, I would say it is for for the pixel in the remote sensing, they are quite, could be the same type of features exhibit different pixel values. For example, the pixel in red circle and the blue circle are all flood waters, but you can see they exhibit different pixel value here. And for the if we utilize traditional machine learning for disaster mapping, one of the critical limitation is that it requires handcraft feature engineering to extract the useful features. For example, for the flood mapping, we typically rely on spectral indexes such as the normalized difference water index, since water is quite sensitive to the green band and the near-infrared band. And along with the spatial structure temporal change features, we feed into different machine learning models, such as support the vector machine random forest, which then can automatically classify a pixel or region as flooded or non-flooded. However, such approach is time-consuming for the feature engineering and the case-by-case effort. In addition, it always produces low performance due to the noise and shadow casted on the remote sensing image. And also, it is very difficult to capture detailed texture and age structure information from the remote sensing image. Right now, we also utilize deep learning-based model that can automatically discover the image representation from the raw image input. For example, based on the red, green, blue, and near-infrared band, we can automatically learn the feature through the hidden layers and produce the output, which again is the result indicate the probability of flooded or non-flooded pixels. The major issue of the deep learning-based method is that it requires typically a large number of samples in order to generate a good, robust machine learning model. In my lab, for even my students with, I would say, domain knowledge, it can take him more than 2 hours to label an image of 1024 by 1024 image. So it's really time consuming to label and massive labels to train the deep learning model. The next challenge is poor model generalizability or transferability. By generalizability or transferability, we mean that if we train our model on one disaster event on one location, for example, we utilize Hurricane Harvey at Texas area to train our model. The model generally cannot perform well in another location, such as for the Hurricane Florence at North Carolina area. The next challenge, I would say, that's applicable for any application rely on the remote sensing image is the low resolution. We know that a remote sensing image has 3 key features, including the spatial, temporal, and the spectral resolution. Unfortunately, due to the technical constraints, the design and utilization of remote sensing image always limited in the trade-off in spatial, temporal, and spectral resolution. For example, if we have a high spatial resolution, which is always likely associated with low temporal and spectral resolution, here I ask the ChatGPT to generate the common spatial and the relation of spatial resolution and the temporal resolution for the image I typically utilize. Even though it's not highly accurate, but I will take it since it's take much faster time to generate. And you can see some of the image like the ghost, you can get the one ghost observation in 5 to 15 minutes, depends on which band, and also the ghost image. However, it has low spatial resolution, and again, it's between 1 and 2 kilometers, depending on which band you are using. Some of the images, such as the Sentinel-2 and the Landsat, it has relatively high spatial resolution, but you can see the revisit date temporal resolution is pretty low. So advanced machine learning and AI model is needed to fuse all those multi-sensor data sets in order to produce real-time high spatial and temporal disaster mapping. Now, let's look at several case studies to see how can we address all those challenges. One of the research projects we have done is develop supervised learning based on deep learning, but our innovation is we only utilize a few human labels. The idea is that we first divide the pre and the post disaster image into patches, and we classify each patch as flooded or non-flooded by calculating the similarity and evaluate the similarity of the pre and the post disaster image patch. If more similar, is less likely flooded, right? And in particular, to let the model know the scenario, we first give the pre and the post flood image pair. And in the encoding model, we go through 3 layers of convolutional layers, pooling layers. And at the end of encoding component, we can connect the learned pre and post image features, which then go through decision component through several dense neural network layers, which can do binary classify, identify one pixel whether it is changed or not, which means flooded or not flooded. For the case study, we utilize 2 hurricanes. One is the 2017 Harvey in Western Houston, Texas area. The second one is 2018 Florence in Lumberton, North Carolina regions. The remote-sensing image we utilize is a commercial satellite planescope produce a spatial resolution of 3 meters by 3 meters. We also manually label ground truth to indicate flooded location to train our model. The result indicate that for both case studies, our model achieved much better performance compared to the traditional machine learning model, such as support vector machine, decision tree, random forest, and ADA boost, which is either low in the precision or recall, indicate that there are a lot of false positive or false negative generated in the process. Even with only 1,500 labels, our model can achieve more than 93% overall accuracy. The result we further evaluate with a different number of training samples from 100 to 2,000 indicate that actually include only 500 patch labels, which can be quickly labeled in 30 minutes by my students. And the model can take only 50 minutes to train the PassNet with 1,500 samples and 1 minute to produce the flood map in western urban Houston area. The second one, even though PassNet can achieve good performance with a few labels, but still include the labels, which limit its application in real-time operation. Therefore, we develop a second model, which is called a self-supervised learning model, patch change vector analysis through a supervised autoencoder. So the key idea is first, given the pre and post disaster image, we cut them into non-overlapping patch, with each patch including about 10 by 10 pixels. And through the encoder, we can extract the representative features. How we do that? Again, we utilize the autoencoder model architecture, including the encoder and the decoder. How it works, basically, given the pre and the post disaster image patches, our model try to compress the features to meaningful and representative features. And based on in the decoder, we try to recover the original features. Through this training process, the encoder learns to extract the most meaningful features. And then we utilize the trained encoder to extract our feature, which perform change vector analysis through different thresholding method and produce a binarized flooding map. We also add 2 additional operations, spectral and spatial filtering, to reduce false alarms. And and further enhance the detection of flood. And based on the evaluation of two flood events, Harvey and Florence, the result indicate with the change vector analysis and plus two additional model, spectral filtering and spatial filtering, our model can achieve comparable performance compared to supervised learning, more than 95 of overall accuracy achieved. So the research indicated that a fully self-unsupervised model is possible for high-resolution urban flood mapping without any human labels. Our model can achieve good generalizability across different events, and no handcraft feature engineering is required, and no human labels is required for our work. And in the subsequent work, we further enhance the self-supervised learning with the weekly supervised learning framework. What we call weekly label is that the labels are automatically generated by the computer or models. And since those models, without going through the rigorous human examination, they potentially not 100% accurate. However, the benefit of a weak label is that we can generate massive labels through our batch process, and therefore can still, with those unlikely 100% labels, but massive, we still can be able to train a relatively decent machine learning model for the flood mapping. How we do that? We integrate different information or knowledge to guide our weekly label generalization or sampling. First, we utilize spatial information from the FEMA flood hazard layer DEM or Microsoft building footprint, and we can identify location with high risk of flooding, which is potentially weak labels of flooded area. And we do the change analysis indicating potential change, which is flooded area for another layer of weak labels. And we also analyze the spectral information based on spectral clustering. Basically, water are clustered in the several category, right? And we also utilize water index, spectral index to generate initial water cluster. And combine all different layers, we generate weak labels of flooded location and non-flooded location. With those weak labels, we then can train different machine learning models, utilize, for example, support vector machine random forest. So this figure shows different output of our weak labels through different processes, spatial, temporal, spectral, and combine the weak labels to train our models. In our work, we generate massive weak labels, actually more than 200 million samples across 13 locations with diverse geographic environment context over 8 flood events. Based on the evaluation of 2 sites in the hurricane forest, we indicate our weak label actually more than 99% of accurate and achieve one score of more than 97, which means our label are highly accurate enough. And then based on we train our model based on those weak labels, utilize different models such as support vector machine, random forest, multi-layer perception. And then we apply this model to do the flood mapping for different locations across different continents, including China, Germany, and Sudan, and Argentina, indicated that our model can achieve global flood mapping capability without any human label, but of course rely on the weekly generated labels. In addition to the flood mapping, we also do the damage assessment work. Basically, here I will focus on introduce on the building damage assessment, physical infrastructure damage after natural hazard. Basic building damage assessment can be categorized into 2 tasks. First is given the image after disaster, right? You need to identify where the building is. We call this building localization or segmentation. Second task is damage severity classification. For each building, we need to classify it whether it's no damage, minor damage, major damage, or completely destroyed. So again, here I'm come back to the self-supervised learning framework, which is kind of, I would say, the most advanced model that address reliance on the massive labels for deep learning model framework. So basically, how does self-supervised learning works? Let me go in a little bit of technical detail. First, it includes two stages. The first stage is the pre-task stage, which means we have utilized pre-training model to extract the useful feature from the massive unlabeled data sets. And once we trained the model, and then the second step, we can utilize the pre-trained model to help us to extract the useful features from data sets with labels. And through the downstream task, our model is retrained and fine-tuned for different downstream tasks such as building damage assessment. So now the question mathematically to describe is that we need to solve the pre-task and make sure our model can extract useful features to give any image, right? So how we do that? Typically, there are many methods to achieve this goal. One method is we can add a noise to the initial image and produce corrupt image. And then the encoder help us extract the feature, right? And the decoder will try to recover the clean image from the corrupt image. Through this training process, the model encoder learn how to extract the useful representative image representation as a feature for downstream task. Basically, after the pre-training model is fully completed, then we utilize the encoder trained in the pre-task and to extract the features in the downstream task. And the decoder, given a small number of labels, can be fine-tuned and retrained to make sure it can perform downstream task. Okay, so go to our task of building damage assessment, right? So given the massive unlabeled data sets here, our first task is add noise, which we utilize Gaussian noising strategy, either noise here, and then we have encoder and the decoder architecture, right? The encoder trying to extract the compressed features, and the decoder trying to utilize extracted feature to recover original image. Through this process, the model encoder learn to extract the most representative features, and then the encoder after pre-trained then transfer to the downstream task. And given a few labels in building localization and segmentation, our model can learn how to identify the location of buildings and classify buildings into different categories. And here is some of our research results compared to state-of-the-art models utilize different model. The result indicated that our self-supervised learning framework can achieve high accuracy for both tasks, building localization and damage severity classification. Next, I would like to focus on in addition to that, I would like to describe a little bit about the research on the wildfire as well. So first research task we do is detect the wildfire burned area or based on the bitemporal unit with attention and tailored loss function. And our model actually intends to address three key challenges in the wildfire burned area mapping, including imbalanced training sample, which means in the training sample, we always notice that burned area are majority sample and burned area are minority sample, which make the model bias towards the unburned training samples. And the second one is boundary area, which you can see the boundary area is always have a mixture of burnt and unburned pixel, make it very challenging to detect. In that case, we integrate the attention mechanism to make sure the model can pay attention to boundary area. Third, our model is applicable to location of diverse geographic and environmental context, which means our model can achieve good generalizability and transferability. So based in this research, we rely on the Senti Level 2, Level 2A product with a spatial resolution of 20 meter by 20 meter. And so the training area, we utilize the Chico, California wildfire, and we test the model trained by the California wildfire in different locations, including Australia, Spain, Indonesia, and Kenya. The result indicate that our model, compared to the baseline algorithm, increase the performance by more than 11% in terms of overall accuracy. In addition to identify the burned area impact, bio-impact area, the next research actually is classify those burned area into different categories, into low burnt, moderate burnt, and severely burnt locations. How we do that? In addition to integrate the pre-fire and post-fire, we also integrate spectral index layer like the normalized burn ratio index and the difference normalized burn ratio index. And our model integrate not just attention but residential speed connection layers. In the end, our model actually outperform other image segmentation model with over with more than 84% of accuracy in terms of F1 score and 74% in terms of mean intersection of union. One of the issue we observe based on our previous severity detection model is that the moderate category is always have low performance. It's less than 70% of accurate we can detect such category. This is because it's overlap with the severe and the low burned categories. In order to address these issues, we are working on a multitask learning framework. The model is the architecture we leverage is called the multi-gate, the mixture of experts model. So this is the multitask learning architecture specifically designed to enhance multi-class classification accuracy. Basically, the idea is that instead of utilize one model classify the pixel into different categories, right? The multi-gate mixture of expert is we include multiple expert network. With each network focus on one specific category, highlighting its difference between that category and other category. So in the end, based on our current result indicate that our MIOU further enhanced 10% compared to our previous model, which is a significant enhancement by leveraging that the multitask learning. And for the rapidly active fire detection, we mostly utilize GOES and WIRS time series data and fusion. So the issue is the motivation of this research is by the limitation of the coarse spatial resolution or temporal resolution of existing active fire product. For example, the GOES image actually empowering the NOAA next generation fire system can provide fast, quick observation in 5 minutes, but it has low resolution, which always result in the false alarm and the emission of small and low-intensity fires. And the Wildfires data product with a relatively high resolution, 375 meters, powering NASA fire information for resource management system. However, it only provides 2 observations per day. So my goal is integrate both products through the data fusion process. In that case, what we do is we develop an auto-encoder architecture based again from we compress those image into the most representative feature. And from this feature, we let it recover the resolution to the Wildfires resolution to achieve both real-time and high spatial resolution active fire detection. And for the super resolution, I would say it has a huge application, not just for fire, but it can apply for many applications. Therefore, our lab has fundamental research is trying to enhance the spatial resolution of remote sensing image, utilize different generative models. For example, not just utilize autoencoder, variant autoencoder, but we also develop a game-based model, generative adversary network model, and the recent diffusion model, which I would say is state-of-the-art model for the super resolution. This is done from the original input, we go through a series of noising process. At each step, we add some noise about 1,000 times. And then we go through the reverse process. At each step, we remove the noise, try to recover the original image. Through this process, we train the model for the super resolution. And the result indicate that the game model generally can generate high quality samples or output with the super resolution. And variant autoencoder typically generates a sample of high diversity. And the diffusion model actually can strike a balance, achieve both high quality and diversity image of super resolution. Even though it takes a long time to generate, as we can say 1,000 steps. And so it is a slow sampling process, but the quality is high. And so as I mentioned, the super resolution, the model can applicable for many applications, not just fire. It can do the flood mapping, air quality, precision agriculture. Here is a set of the image we generated based on different super resolution model. For one of my research work on precision agriculture, we utilize enhanced model telescope satellite image, which typically is not high resolution enough to do the field plot level phenotyping. But through the super resolution, we can generate 75-meter resolution telescope image for different phenotyping tasks as well as year prediction. So for the wildfire progression model, we also done some work. And this fire progression model can be framed as a time series model and a forecasting task. Basically, given as historical the image indicate the fire front location, right? Our task is predict the next location of those fire front in next time interval. So basically, we have implement convolutional long short-term memory, and which combine the benefit of both convolutional layer to capture the spatial dependence within one image, and we utilize LSTM, long short-term memory, to capture the temporal dependence across different image sequence. And right now we are working on attention-based graph neural networks. Basically, the new idea is we trying to model the fire front as graphs and utilize attention-based graph neural networks to do the prediction. What is the fire front for the image in the next time sequence. And so next, let me quickly introduce some of my work in utilize social science, which means utilize the social media, internet data sets to do the disaster mapping and the damage assessment. So basically, similarly as the physical sensor data sets, remote sensing image, the social media data sets also have major challenge we need to conquer before we utilize them for our research. The first famous challenge I would say defined as the 5 ways from a massive volume. For example, it generates 400 million tweets now is X-ray per day many years ago. But I believe now much more tweets can generate per day. And those tweets are generated in high speed dynamically every second in different data formats such as text, photo, video. And also those data sets, since the authors, the information are not validated, so create trust issues. The last way I would say is the most challenging part is giving you the data sets. How can you extract the information, build the knowledge to for your application? And in fact, the information we define during the natural hazard is called situational awareness information. Information such as damage, donation, offer, information source, resource request, caution, advice, fatality, injury, missing people are all considered as useful information contribute to situational awareness establishment. Unfortunately, during our analysis in the Hurricane Sandy indicate that only 2%, 70% of data sets are related to the hurricane highway. And less than 1% of information actually are related to situational awareness, which means contribute to the disaster management. So the challenge is how can you, from the massive data sets, we can extract the useful information. Some of my work we can see is that one of example is, I would say very interesting example is given the image of posted from social media or internet, we can do the flood depth estimation. Basically, what we do is we extract the reference object such as building, human, car, traffic sign, and lamp post, and we identify the proportion of object above and below the flood. We identify flood depth. For example, if we are extracting human bodies, we typically extract their head, shoulder, and knees. And then based on those key features, we know what is proportional for body under the water, right, to detect the water depth. Another example is not just utilize the image, we also utilize textual information in the multimodal learning to extract the useful information from the massive social media data sets. We specifically will go through 3 steps or tasks. The first task is we identify disaster relevant information from massive data sets, and for those disaster relevant information, we further categorize them into different categories such as infrastructure, utility damage, rescue, volunteer or donation, vehicle damage, infected individual. For those the information or image related to damage, we classify them further into different damage level, minor, major, complete, destroyed category, and used for the extract situation awareness information for disaster management. In another work, we utilize self-supervised learning for real-time classification of disaster photos on social media and the news. So the idea is, again, through the pre-training task, we learn how to extract the useful features from the any image, right? And then we automatically, based on the extracted feature, we to do the classification, the image into informative or non-informative categories based on the comparison with the self-supervised learning and the supervised learning. Our model, even though not achieve quite high as supervised learning, but very close. So basically, I would say based on my research experience, we actually witnessed several development and advancement patterns in the last 10 decades, which can be summarized from the data methodology application. First, for the data sets, we see that we now collect a massive number of data sets from both social media planner and physical sensing network. And the traditional we rely on for rating for data source or official data source from the USGS, NOAA, NASA to do the classification. The flood mapping or wildfire detection. But now we also rely on crowdsourcing data sets, which are dynamic, generated in heterogeneous data format and unstructured in nature, which called advanced methodology in order to extract those useful information in a quick fashion, right? So methodology-wise, we do see some advancement as well. In traditional, we rely on handcraft feature engineering to do thresholding method to extract the flooded area or wildfire, active fire locations, and then we feed those more features into traditional machine learning models such as the support vector machine random forest. And now we rely on deep learning based model to automatically discover the features, to learn the feature for different application. And instead of rely on supervised learning, which require the human labels, we are more and more rely on self-supervised learning or weakly supervised learning. And in traditional, we may utilize a single data source or single remote sensing image, text or photos to do the data mining. But now we leverage multi-source data, multi-sensor data, and in the data fusion to achieve better accuracy. And traditionally, I would say in geography, we most apply the machine learning and AI technology. Now we are enhance the AI machine learning with the spatial data sets, spatial principles, which we call GeoAI. And in future, I'm hoping, actually, I think that will be the future direction is that we're gonna develop a more explainable, generalizable, and interpretable prediction by integrating, for example, physical process-based model and the data-driven models, make the result achieve better performance, yet the result is interpretable. And so based on the advancement of data sets and methodology, I think we also see now from the low resolution, now we can generate high spatial resolution, real-time disaster mapping, and applicable for global area. Well, that's my summary, and take this opportunity, I want to thank my students and the sponsors. Any question, happy to answer.
Great, let's thank you, Qunying, very much. Thank you for the really nice talk. Any questions?
Yeah.
Maybe I just didn't catch this when you were talking about like trying to predict where the fire is going to be in the future. That's really cool. Were you just using like imaging tools, or were you also using like I don't know, like WRF model output? So like getting some information from physical variables.
Yeah, I think that's a very good question. Due to the time constraint, I didn't cover that aspect yet. But definitely, like the wildfire, not just impacted by many factors like vegetation, fuel, right, wind, and also the precipitation, many climate effects. So that's our next step, is really integrate those facts into our, in addition to sensing image, but you can also get other data sources into the modeling process. That's one aspect. Another aspect is we really can integrate the physical process-based model, because the observation we we have different data sets, but it's static. But if we integrate physical process-based model, it can produce the features, and we can also integrate the prediction output coupled in our data-driven model and have better performance. Yeah.
Thank you.
Yeah.
It seems like for your flood mapping and your burn scar, except for the burn intensity part of it, it's the same problem. And I'm wondering why you had different machine learning models to approach that.
That's a very good question. I think fundamentally because it is because of the data sets. And for the flood mapping, because it's not like a urgent flooding, it's not like a quick evolution like a flood. So the wildfire, we typically leverage like a ghost product is 2 kilometers. And for the urban flood mapping right now, I think majority of our research leverage much higher resolution data sets, but with a lower temporal resolution, like a Sentinel-2, it has 20 meter, 10 meter resolution. So basically, therefore, the wildfire, active fire detection.
No, I was thinking more the burn scar. Because they're both looking at changes in the land signature,
Oh yeah.
and they're both using some kind of a spectral approach to.
Yeah, exactly. Yeah, I see what you mean. Like for the burnt location, indeed those models can be interchangeable for different case because they both utilize the Sentinel-2 data product. But the major issue is when we need to pay attention to the spectral band used for different application, because wildfire and also the flood are sensitive to different band.
And then I have a kind of philosophical question. So on the more the social media aspect, so more and more AI is getting embedded in social media. How does your AI untangle social media with your AI generative? You showed, for example, that only less than 1% of the social media actually had to do with flood damage. Is there a point where AI is going to have to figure out whether part of what it's seeing is AI generated?
Oh, you mean like the AI model can help us detect
Something like that.
Yeah, definitely. I think right now the AI. I would say now there are many models you can integrate the advanced foundational model to detect the useful information. For example, in our work, we also now utilize the ChatGPT can help us analyze the image as well to extract the useful information. Jack?
Nice talk, Qunying. With your work in sort of advancing methods, are you or your collaborators also working in turning this into sort of operational applications, moving from the what you showed here to sort of getting into decision makers' hands?
Yeah, actually, that's my goal. And right now, I think Brad and I are collaborating together, trying to, like, if the wildfire, active fire detector, if we eventually can enhance the existing fire detector product, we will integrate it possible into the operational. That's my goal.
So we have a question online that I'll sneak in here. So this person is curious about the details of conducting satellite data fusion. Could you give more information on how VIRIS works in your machine learning model?
Okay, I think that's a very good question. So basically, idea is we have the low resolution data sets, right, from GOES, and it's 2 kilometer resolution. And we have training is the various high resolution data sets. And so basically the idea is given the low resolution data sets, we compress its, extract its features and let the model to generate a higher resolution data product. And through this process, given enough training sample, the model lens now give any image with low resolution, it will generate a higher the image of a higher resolution. Yeah. So that's one of the typical architecture of the super resolution model.
For your presentation, since your work on this coding rely on remote sensing images as the input, so I was wondering, do you need any, because remote sensing images sometimes come noise, so do you need to consider the unstable errors in remote sensing images before you put them into your different networks?
Oh, that's a good question. I think we, in our model, we assume the remote sensing need to go through many pre-processes like the calibration, correct the atmospheric and also different errors, remove the cloud, and but in our research we just assume those processes are already done, but definitely there are many work to simply just remove cloud. It takes a tremendous effort to correct all those issues before you can leverage the data sets for subsequent downstream tasks. In our case, for example, in order to get the image for flood mapping, and actually we need to capture different time scales until we find a perfect image for our case studies. Yeah, and also I think that's one of the reasons in our future research we also intend to address some fundamental issue reason from the remote sensing data itself, not just low super resolution, but also all those potential errors, especially the cloud. In many, you can see like 60 to 80% of image are not usable because of covered by the cloud. Yeah.
Any last questions? Okay, well, let's thank Qunying then again.